For week 4, we're going to start discussing probability distributions. Now remember last week we looked at basic probability and I mentioned probability distributions. Probability distribution, remember, is the whole sample space. Oops, let's get back here. Get my pen. It's the whole sample space. And then the probability of each of those events within the sample space. For example, let's look at rolling a fair six-sided die. So the possible events in the sample space, we can get a 1, 2, 3, 4, 5, or 6. The probability of each of those events, so I'm just labeling each event x, the probability p of x then is the probability of each of those events. Well, to get a 1 is 1/6, to get a 2 is 1/6. Each of them, since they're all equally likely, has a probability of 1/6. To be a valid probability distribution, two things have to be true. Each of these values, each p of x, has to be between 0 and 1. All of those are 1/6 or 0.1667. Those are all between 0 and 1. So that part is valid. The other thing that must be true is the sum of those probabilities must equal exactly 1. If all of the probabilities, all the events in the sample space, one of them must occur. So the probability that at least one of them must occur is 1. Remember, this would be the equivalent to the probability of xi or x1 or x2 or so on, all the way up to, so remember, or means one or at least one of them must occur. So let's look at some standard probability distributions that we have out there. Let's explore some of the vocabulary behind it. We've talked a little bit about random variable. Examples, a grocery store manager might be interested in the number of broken eggs in a carton. So there's a dozen eggs in a carton. Or an environmental scientist might be interested in the amount of ozone in an air sample. Each of those is a random variable since we cannot predict it until it happens. There's a level of uncertainty in it before we actually collect that sample and take those measurements. So the random variable is a numerical value whose value depends on the outcome of a chance experiment. It associates a numerical value, we associate a numerical value with each outcome of a chance experiment. So there are two types of random variable. There's a discrete and there's continuous. And we've looked at those terms before. Discrete means there's gaps in between or sometimes countable. Continuous means it's measured or there's no gaps in between. There's always room for values in between. The big distinction with discrete is the probability that x equals a certain value is always 0 because discrete has an infinite number of possible values. You can't assign a value to a specific, or a probability to a specific value. Probability only applies to ranges of values in a continuous distribution. This week we're going to focus on the discrete distributions. Two types of the random variables, the discretes and the continuous. We've already looked at these. Remember, discrete means that they can be counted, and there's gaps between them when we plot them. Continuous is all the possible values on an interval, so it's an interval rather than just the points within that interval. Again, typically measured. So in this chapter, we're going to look at different distributions, discrete and continuous. For week 4, we're only going to go up through section 7.4, so that's the discrete distributions. So we're going to identify the following variables as discrete or continuous. The number of broken eggs in a carton, can't have half a broken egg. It's either broken or it's not. That's discrete. The amount of ozone in a sample of air, that's continuous because whether we're measuring by milligrams or whatever, milliliters, it's a measurement of some sort. The only way we could make that discrete is if we're actually counting particles, which technology kind of limits us in our ability to do. The weight of a pineapple, this is a measurement. It is continuous. The amount of time a customer spends in a store, this is also a measurement. It's continuous. Number of gas pumps in use, well, can't be half a gas pump in use. That's counted. That is discrete. Probability distributions for discrete random variables. There's a few that we're going to look at. Probability distributions model and describe the long-run behavior of a variable. So it's like we said, it's all the possible results and their probabilities is what a probability distribution is. So in a Wolf City, a fictional place, regulations prohibit no more than 5 dogs or cats per household. So let X equal the number of dogs and cats in a randomly selected household in Wolf City. Is this a discrete or continuous variable? It's discrete. You can't have half a cat or half a dog. Possible values? Well, you could have none, and you can't have more than 5. So 0, 1, 2, 3, 4, or 5. The Department of Animal Control has collected data over the course of several years, and they have estimated the long-run probabilities for each of those values of X. That if we randomly select a household, it's a 0.26 probability that house has no pets. 0.31 probability that house has 1 pet and on up. 0.03 probability that house has 5 pets. What do you notice about the sum of them? Well, we talked about that before. If we add those up, that better equal exactly 1. This is called discrete probability distribution because it has separated values, and it can also be displayed in a histogram with the probability on the vertical axis. So you got 0, 1, 2, 3, 4, 5, labeling those different things, and those are the probabilities. Again, the area of those should add up to 1. You can think of that histogram as being area. It's 1 unit wide, and the height is the probability, so the area of it is actually the probability of that value. So a discrete probability distribution gives the probabilities associated with each possible value of that random variable. Each probability is the long-run relative frequency, if it's in many cases. Otherwise, it can be done theoretically for, again, certain special distributions. Usually displayed in a table, but it can be done with a formula or a histogram. So properties of discrete probability distributions. First of all, as we mentioned before, all probabilities, each individual probability must be between 0 and 1. And the sum of the values has to be exactly 1. So for this, we notice all of them are between 0 and 1, and they add up to exactly 1. So let's see, what is the probability that a randomly selected household in Wolf City has 2 pets? That's 0.21. So it has at most 2 pets. Sorry, that should be 0, 1, or 2. So 0.26 plus 0.31 plus 0.21 gives us 0.78. Now, notice that said at most 2 pets. So 2 would be at most 2. That was part of it. Now we change it slightly. It has less than 2 pets. That does not include the 2 anymore. 2 is not less than itself. So that's only 0 or 1. So the 0.26 plus 0.31 is 0.57. Very subtle difference, but that's very important as we move forward to know the difference between less than 2 and no more than 2, or at most 2. What is the probability that a randomly selected household in Wolf City has more than 1 but no more than 4? More than 1, so that means it doesn't include the 1. No more than 4 could include the 4, so it's those 3 that we would add together. So again, you got to be very careful with that wording. It's greater than 1. It doesn't include the 1, but it is less than or equal to 4. It includes the 4. We add those up to get 0.40. So when you calculate these probabilities, you must pay close attention to those end conditions. Is it greater than or equal to, or is it strictly greater than? And do we include those endpoints in our calculation? Probability distributions for continuous random variables. So consider the random variable. X is the weight in pounds of a full-term newborn baby. This is a continuous variable. Again, continuous variables are next week, but we're going to just do this quick little overview here quick. It is measurement. Weight is a measurement, so it's continuous. Suppose that the weight is reported to be the nearest pound. The following probability histogram displays the distribution of weights. So 4, 5, 6, 7, 8, 9, or 10, just rounded to the nearest pound, would be the distribution. Area of each rectangle, of course, is the probability of being within that weight zone. 7, of course, represents 6.5 to 7.5. The sum of the areas of all those should add up to 1. Now suppose that the weight is reported to the nearest 0.1 pound instead of the nearest pound. So instead of rounding to the nearest pound, we round to the nearest 10th pound. We get a histogram. Now they don't even draw in the vertical lines for those bars, but they are there. You can see it's very tight together. Those bars are very tiny. All you basically see is lines up there. But what you really see here is that this is now starting to take on that bell shape that we've talked about before. Rectangles become smaller and smaller, it's going to actually become that curve. That is that normal curve we've talked about, that smooth curve. But notice, even though we don't have bars under there, the probability is still represented by areas. The probability of being between 6 and 7 pounds, or 6 and 8 pounds, is the area under the curve between 6 and 8. So this is what we call a probability density curve. The area under the curve, again, between the desired values represents the probability of the random variable being between those desired values. So more on our continuous variables. It's specified by a curve called the density curve. The function that describes this curve is denoted by f of x, and it's called the density function. The probability of observing a value in a particular interval, remember we don't look at a single value for these anymore, you have to have an interval, is the area under the curve in that interval. So other properties of continuous functions. F of x greater than 0, the curve cannot dip below the horizontal axis. So the probability of any event, and that event has to be an interval, has got to be greater than 0. Of course, it also has to be less than 1, by the way. The total area under the density curve equals 1. So let x denote the amount of gravel sold in tons during a randomly selected week by a particular sales facility. Suppose that the density curve has the height f of x above the value x, and here's our function. F of x is 2 times x minus 1 for x between 0 and 1, and 0 otherwise. So that's our density curve. So what is the probability that at most 1/2 of a ton of gravel is sold? So there's 1/2. At most means 1/2 or less. So that's that area right there. So we've got a height of 2 here and a height of 1 there. 1 plus 2 is 3, divided by 2 is 1.5. Area of a trapezoid formula. 0.5 height here, so that's going to be 0.75 as that area comes out to be. That's our trapezoid area formula that I just mentioned. So there he is. We find that area of 0.75. Now they gave the trapezoid formula, but then they also came back and said, well, let's just use a triangle formula and cut this back to a rectangle that's 1 by 1/2. That's the 0.5. Then we have a triangle here that's 1 high by 0.5 wide, so 1 times 0.5 times 1/2 to give you that 0.25 for that. Okay, so what is the probability that exactly 1/2 ton of gravel is sold? So exactly that amount, well, that's going to be 0. The probability of exactly any amount is 0, because a line has no width. It has no area. Again, that's because there's an infinite number of possible values. The probability of a single value has to be 0, because if a single value has a probability, then the probabilities under that curve would add up to be more than 1. What is the probability that less than 1/2 of a ton of gravel is sold? So here's 1/2. We're looking at this probability. Now remember, since the exactly 1/2 has no probability, the probability of being less than 1/2 and the probability of being no more than 1/2 are going to be the same. That's one of the big differences between the discrete distributions and the continuous distributions. In the discrete distribution, there is a big difference between p of x less than a value and p of x less than or equal to a value. Those are very different in a discrete distribution. In a continuous distribution, those will have the same value. P of x less than 1/2 is going to be exactly equal to P of x less than or equal to 1/2. So we see that they're the same. So it's still 0.75. Suppose x is a continuous random variable defined as the amount of time in minutes taken by a clerk to process a certain type of application form. Suppose x has the probability distribution here that 0.5 if it's between 4 and 6, and 0 otherwise. This, by the way, is what's referred to as a uniform continuous probability distribution, because we got 4 here and 6 here. There's 5. The height is 0.5. The area of that rectangle is going to be 1. It's 2 wide and 1/2 tall. 2 times 1/2 is 1. So that works out that total probability is 1. So they just used the line I boxed it in. That's just what I'm used to doing. It's a box or a flat line on our graph for our density function. So what is the probability that it takes more than 5.5 minutes? Well, 5.5 to 6 would be that range. So it's 1/2 tall, 1/2 wide. That's going to be 0.25. Now another way of doing a uniform probability like this is to look at intervals. Like I said, this is called a uniform distribution. On a uniform distribution, they sometimes look at intervals. So they might say that the probability of x being between a and b is the range b minus a over the total range of the distribution, the max minus min. So in this case, being greater than 5.5, that's really being from 5.5 to 6. So that'd be 6 minus 5.5 over 6 minus 4. Gives us 0.25. Just an alternative way of finding probabilities from a uniform distribution. Other density curves. Well, this is actually a skewed curve. It's still looking at the area underneath the curve. Now we will have tables that'll show us how to find that area. We're not going to have to calculate it ourselves. Also, we have calculators that do that for us. This actually looks kind of like a chi-squared distribution, inverse chi-squared distribution. So what is the probability that a continuous random variable x lies between a lower limit of a and an upper limit of b? Well, what we generally do, most tables only give us the probability of being less than a value. So to say it's between two values, we take the probability of being less than the larger value and we subtract the probability of being less than the smaller value. So probability of being between a and b is the probability of being less than b minus the probability of being less than a. That's going to be useful for us if we use the probability table for normal distributions. Now, I mentioned normal distributions. Normal distributions, if you have the TI-84 calculator, really I don't see how you can get through the course without it, so something to have. The TI-84 calculator has a built-in normal function that does that calculation for you. So means and standard deviations of distributions. The mean of the random variable x is often called the expected value of that variable. It is the center of that distribution if we graph it. Standard deviation, again, is that variability, how spread out it is. Like I said, the mean is sometimes called the expected value, which tells us what is on average, what would we expect the value to be. In other words, if we repeat this over and over again and take those results, on average, what would we expect that result to be? For example, the expected value of rolling a die is 3.5, a 6-sided die. If we rolled the die over and over and over and over again, recorded each of those values, and we found the mean of them, it would be 3.5. So the expected value is the sum of the values times their probabilities. Variance is calculated using basically it's the standard deviation or variance formula from before. A little bit longer process. Standard deviation, of course, is just the square root of the variance. So dogs and cats revisited. So here's our distribution. To find the mean, we're going to multiply each value by its probability. 0 times 0.26 is 0. 1 times 0.31 is 0.31, and on down the line. If we add all those up, that is our expected value, or the mean of that distribution. The standard deviation's a little bit more work. So we have to look first see how far each deviates from our mean. So we've got 0 minus the mean of 1.51. We square that and multiply by our probability. Very similar to doing a standard deviation for a frequency table. So then we take the second value of 1, we subtract our mean of 1.51, we square it, times its probability of 0.31. We do that for each of them. We add it up to get 1.7499. That is our variance. And of course, to get the standard deviation from that, we square root it. So 1.323 is the square root of 1.7499. So for continuous distributions, the mean locates the center of that curve. Standard deviation, again, is the spread, how spread out it is. Company receives concrete of a certain type from 2 different suppliers. X is the compressive strength for supplier 1, Y compressive strength for supplier 2. Suppose that the average compressive strength is 4,650 pounds per square inch with a standard deviation of 200 pounds per square inch. For supplier 2, it's 4,500 pounds per square inch with a standard deviation of 275 pounds per square inch. So the first supplier has a higher mean and less variability. That, to me, would be a good thing. Higher average and less variability. So let's graph those. So we've got the curve. This is supplier 1. That's the mean is the center of the curve. The standard deviation spreads it out. This is supplier 2. They have a lower mean and it's more spread out. To me, supplier 1 is still definitely more desirable. Let's go back to Wolf City. The grocery store had a total of 14 employees. The following are their salaries, monthly salaries for each employee. The mean and standard deviation of the salaries. Mean is $1,700. Standard deviation is $603. Suppose business is really good, so the manager wants to give a $100 raise per month. The new mean and standard deviation. The standard deviation doesn't change. The mean just goes up by $100. It just takes that curve that was here and it slides it up by $100. Doesn't change its width. Let's graph the box plots for this information. So the first one, notice those are exactly the same, just one is slid over, and the outlier has moved up as well, but there's still just one outlier. Hasn't changed any of the ranges or any of that. So what would happen to the mean and standard deviation if we had to deduct $100 from everybody's salary? Standard deviation would still stay the same. The mean would just shift to the left. Now, on the other hand, suppose the mean gives, rather than giving a flat $100 raise to everybody, suppose the manager gives everyone a 20% raise. Now, both the mean and the standard deviation increase. The mean went from 1,700 to 20% more. 120% of 1,700 is 2,040. 603, the standard deviation also went up by 20%. So it increased by a multiple of 1.2. Well, that's 120%. So if we look at our box plots here, first box plot's the same. The second box plot, this is if we just added $100 to everybody, just slid everything over. This bottom one is if we added 20% to everybody. Notice it spreads everything out and slides it over. Mean and standard deviation of linear functions. So if we have linear functions and we want the mean and standard deviation, let's look at an example here. Consider the chance experiment in which customer of a propane gas company is randomly selected. Let X be the number of gallons required to fill a propane tank. Suppose that the mean and standard deviation is 318 gallons and 42 gallons. So the mean of 318 gallons and a standard deviation of 42 gallons, respectively. Excuse me. The company is considered considering the price model of a service charge of $50 plus $1.8 per gallon, or $1.80 per gallon. Let y be the random variable of the amount billed. So what is the equation for y? $50 for the service charge times 1.8 times the number of gallons. Mean and standard deviation? Well, 50 plus 1.8 times 318 is the mean. So the mean for y is 622.4. Standard deviation, 1.8 times the standard deviation per customer is just $75.60. Notice the 50 doesn't play into the standard deviation, only into the mean. Suppose we're going to play a game called Statland. Players spin the spinners. So the size of each slice of that spinner is the probability of landing on it. So we have two spinners, A and B. A has 4 sections, B has 6. The mean and standard deviation for each spinner, well, the expected value for spinner A is 2.5, for B is 1.118. The expected value for A is 2.5, the standard deviation is 1.118. The expected value for B is 3.5 with a standard deviation of 1.708. List all the possible sums for A plus B. Well, you could have 1 plus 1 would be 2, 1 plus 2 would be 3, 1 plus 3 would be 4, 1 plus 5 would be, or 1 plus 4 would be 5, 1 plus 5 would be 6, 1 plus 6 would be 7. So this is if spinner A is a 1. This is if spinner A is a 2. 2 plus 1 is 3, 2 plus 2 is 4, and so on. This would be if spinner A was a 3. 3 plus 1 is 4, 3 plus 2 is 5. And the last row would be if spinner A was a 4. Then it goes through all the different possibilities of spinner B. Find the mean and standard deviation of these sums. Well, the mean is 0.6, or is 6. Notice that is the same as if I just added the means of the two individual spinners. Because I'm adding the values of the spins to get my random variable, the means is just adding the values. Standard deviations, however, do not just add together. That's a little bit different. Those have to be, notice that the mean is the sum of the means. The standard deviation, however, is not. So let's think about this and return to that standard deviation in just a few minutes. So let's look at the possibilities for A minus B. Again, this is if spinner A is a 1, this is if spinner A is a 2, and down the line. Find the mean, B minus A. So this would be a spinner A. B is a 1, 2, and down. So we find the mean of those differences, it's 1. Well, notice that's mean of B minus the mean of A would be 1. So the mean of those differences is the same as the difference of the means. But again, the standard deviation is not the difference of the standard deviations. Now if we go back here, notice the standard deviation for the sums was 2.004. Standard deviation for the differences, 2.004. So when we add or subtract the values, the means are added or subtracted, but the standard deviations are combined in the same way. So how do we combine those standard deviations? Well, the mean and standard deviations for linear combinations, AX1 plus AX2 and so on. So then the mean is just A times X1 plus A times X2 and on down the line. That's just adding them together times the multiple of however many times they're included into the sum. Standard deviations are found by you combine them, you actually add the variances. That's what this is. Sigma squared is actually the variance, or standard deviation squared. And you add the variances and then square root them to get to the standard deviations. Only true if the values are independent. Those two spinners, one does not affect the other. So suppose, actually let's go back and I want to calculate that from those spinners. So let's see what that means here. So what that means is this is the square root of, each of them is only included once. So it's the square root of 1.118 squared plus 1.708 squared. We calculate that out, we're going to get the 2.041. So, commuter airline flies small planes between San Luis Obispo and San Francisco. For small planes, the baggage weight is a concern. Since small planes have a weight limit, we have to worry about their baggage weight. Suppose it is known that the baggage weight X in pounds is checked by randomly selected passenger has a mean and standard deviation. 42-pound mean, standard deviation of 16 pounds. Consider a flight on which 10 passengers, all traveling alone, are flying. Total weight of the baggage checked, well, it should just be 42 times 10. Should be a total of about 42 times 10, or 10 42s added together. Should be about 420 pounds. The standard deviation in that is going to be that standard deviation of 16 added together 10 times, so there's 10 passengers. Then if you square root it, you get the standard deviation of 50.6 pounds, basically. So now we're going to look at special distributions. We're going to look at discrete distributions for this week. We'll come back next week to look at continuous distributions. I'm going to end this video here, and so I can talk about the binomial and the geometric distributions in their own video.